continuing with section 2.3. This is video part B. And the first couple of examples we did in this section, we were looking at exponential growth. In this section, we're going to look at a couple of examples of exponential decay. So we'll start with a single pane of glass obliterates 3% of the light passing through it. I'd like to find an equation for an exponential function giving the percent, p, of light that passes through n panes of glass. So let's once again make ourselves a little table of values. I think that really helps figure out a problem sometimes. N was the number of panes. And let's see, P is the percent of light. If I have no glass at all, we'd have all of the light. So we'd have 100%. Now we're told that one pane of glass obliterates 3% of the light, so gets rid of 3%. If we get rid of 3%, then what percent do we keep? We'd have to keep 97%, right? So I could say I'm keeping 97% out of that 100, or in other words, I'm multiplying by 0.97. And 100 times 0.97 is 97. That gives me a kind of a way of attacking this problem, though, a technique, right? Because now when I add the next pane of glass, 2 panes of glass, I had 97%. I get to keep 97% of that. So once again, I'm going to multiply by 0.97. And that's about 94.1%. I'll keep all the values in my calculator, but I think I'll just round off to 1 decimal here. I could keep going. If I put on another pane of glass, a third pane, I would once again cut out 3% of the light, or in other words, keep 97%. So multiplying by 0.97 again gives me about 91.3%. And so on. In terms of my exponential function, I'm keeping that 0.97 or 97%, so my base is the constant multiplier, 0.97. And then I've got the starting value, or y-intercept of 100. So there's my a value. So my equation, y equals ab to the x. The y values are p, the percent of light that gets through, equals our a, which is 100, times the b, 0.97, and the x values are the number of panes, n. And so there's my exponential decay function, base less than 1, that represents this situation. Now once again, it's not necessarily true that you would have to write down the table of values. I think it helps especially when we're starting out. But if you recognize that you start with 100% of the light, and the fact that we are getting rid of 3% means we keep 97%, that's your base, you very well might be able to write that function down without ever creating a table at all. All right, our A was 100. At the beginning, which in this case is no glass, we have 100% of the light. And the B is 0.97. And if we think about this very much like we were thinking about it in the last couple of examples, I'm going to say that's the same as 97%. Subtract the 100% that we would have started with, and we get negative 3% is our change. The amount of light is decreasing by 3% for each pane of glass. Again, that was pretty much stated in the problem, but that's how we would find it based on the B in the problem. So the amount of light decreases by 3% per pane of glass. And then finally, we want the percent of light that passes through 5 panes. So that would be n equal 5. And that's just a matter of plugging into our function. I'm going to call it P of 5. 100 times 0.97 to the 5th. And it looks like it's about 85.9%. Of the light remains, passes through. All right, so far we've kind of had the values of A and B pretty much given in the problem if we looked for them carefully, and even their interpretations were very much described for us in the problem. In the next example, we're going to have to work a little bit harder to come up with the interpretations because it's not said in exactly the way that we need it in the original problem. This is a half-life problem. And typical half-life problems involve things like radioactive decay. Radioactive elements have a certain half-life. Or they're often used for drug calculations. Medications have a certain half-life in the human body. As they wear off, there's less and less of them in our bloodstream. So we're going to do a medication problem. The half-life of acetaminophen, which is the active ingredient in Tylenol, is 2.5 hours. That means that if a person takes medication containing acetaminophen, the amount of acetaminophen still in the body is cut in half every 2.5 hours. So I'm going to start by looking for a table of values showing how much acetaminophen is in the bloodstream at various times. All right, and you know what? I think there's something I should have put at the beginning here. Since we're going to go ahead and find our model eventually for a 500 milligram dose, let's assume that right up here. We'll assume that we take a 500 milligram dose. All right, so let's see. I'm going to put my time in hours. And let's call A the acetaminophen in milligrams. At time 0, which is right when we take that dose, we have the entire 500 milligrams. Now, the key to making this table is the concept of the half-life. The amount still in the body is cut in half every 2.5 hours. That means that if I go to 2.5 hours later, I'm going to have exactly half as much, 250 milligrams. If I go another 2.5 hours, so a total of 5 hours, it gets cut in half again. 125 milligrams. Another 2.5 hours. So we're up to 7.5 now. Gets cut in half again. 62.5 milligrams. You get the idea. All right, so be a little bit careful with this one. Notice that although it's tempting to say, oh, B is a half, what don't I have here? My inputs are not going up by 1. So just noticing that I'm multiplying by a half does not define the B value. I'd have to have my T's by 1 hour intervals in order to make that happen, and I don't. So we're going to go ahead and find our mathematical model, and we're going to have to work a little bit harder for it. We'll use the technique we used at the end of the last section, 2.2. I'm going to say y equals ab to the x is our standard exponential function. If you prefer to use the a's and the t's right now, you certainly can. My experience over the years is that most of my students prefer to work with x's and y's and then just change the variables at the end, which is fine. So let's see. We do know the y-intercept, right? There's our a value right there. So I can put that in right away. That's really helpful. And then I'm going to pick one other point to plug in to solve for B. Now it really doesn't matter what other point you choose. I might be a little bit more comfortable with whole numbers, although it's not absolutely necessary. I'm going to choose the 5 and the 125. So I'd have 125 for y equals 500 b to the 5th. All right, I need to solve for b, so I'll start by dividing by the 500. That should be a quarter, 0.25. Let's just double check. Yep, there we go, 0.25. And then we want to raise both sides to the 1/5 power to get the b by itself. And so my b is about 0.757858. Again, keeping a lot of decimal places in the b is important to help preserve accuracy if you're actually going to use this function to make predictions. So let's put it all together. Y is actually A, the amount of acetaminophen. The A value is the 500. The B value, 0.757858. And then the X value is really T, the time. All right, so what are A and B, and what do they mean? The A is the 500, and unsurprisingly, that's just the starting value again. It's how much acetaminophen after no time had passed, or how much acetaminophen we started with, the initial dose. We started by taking 500 milligrams of acetaminophen, if I can spell that again. There we go. For the purposes of describing what's going on with B, I will typically round B off a lot more just so I don't have to keep this whole long thing in my description. I'm going to say B is approximately 0.758 if I round to 3 decimal places. Which I'm going to think of as 75.8%. If I take away the 100% of starting value, we have negative 24.2. Which represents the change. Right? Take our B, take out the 100% that we started with, and that gives us our change. That means the amount of acetaminophen is decreasing by 24.2% per hour, since our units of time in this problem are hours. So this was one where really the B value wasn't in the original problem in any obvious way at all. We couldn't figure that out until we had the equation. All right, and then finally, how much acetaminophen is left after 6 hours? If I just plug 6 in for T, so A of 6 in function notation, and here, when I'm actually making a prediction, I'm going to use all the decimals that I kept. Looks like about 94.7 milligrams. All right. So all the models we've looked at so far have been perfect exponential models. We've had an exact multiplier, and we've gotten a precise model. We'll pause here, and when we come back, we're going to take a look at what happens when we have an approximate exponential situation.